Go.
Hi
Okay.
everyone. Thank you for tuning into my talk today, which is on the Monte Carlo perturbation theory and Monte Carlo Green's functions methods being developed by the Harada Lab at the University of Illinois in Urbana-Champaign. My talk is divided into three sections. In the first section, I want to introduce the general MCMP and MCGF formalisms by quickly going over the derivation of MC MP2. This is to identify some of the key algorithmic steps and objects in the MCMP program. During the second part of my talk, I want to discuss the structure of our program and how modular design has allowed us to implement a full family of methods with ample room to grow in a practical manner. Finally, I want to talk about an area where we've had some growth recently, which is looking at applying the MCMP methods to calculate dimer interaction energies. For technical reasons, this isn't quite as simple as running three separate calculations, but the modifications that we needed to make were very easy to implement. I want to first establish the basic type of Monte Carlo integration problem that we're pursuing with a toy example. So here we have the integral of some function f over some set of coordinates x. The first thing that we do is to introduce a probability distribution into our integration. And then we exploit the stochastic meaning of this integral, which is the average value of f divided by omega when the coordinates x are distributed according to the probability distribution function that we introduced. We can produce an estimate for this value by generating a large number of coordinates and then evaluating the integrand f divided by omega and taking the average. This estimate, of course, has an associated statistical uncertainty, which is equal to the square root of the variance divided by the number of samples that we accumulate. The variance is a property of the particular integration problem that we're trying to solve, and here is given by the expression in the bottom right corner of the slide. From this toy problem, we see that the two requirements to perform this type of Monte Carlo integration are to have knowledge of our integrand f, as well as establish a suitable sampling distribution omega. All of the MCMP and MCGF methods have a very similar construction, the simplest being MCMP2. We're going to look at one path to determine the integrands for these methods, which starts from the textbook expression for the MP2 energy. This particular set of expressions assumes a restricted Hartree-Fock reference and is already spin adapted. The derivation is one term at a time, so we'll proceed with only the direct term. The first step in this derivation is to switch to the Laplace transform formalism of Alaimov. In this formalism, we rewrite the energy denominator as an integral over an exponential function, and that gives us this expression for the direct term. Next, we expose all of the integrals in the two electron integrals, and at this point we do have a satisfactory form for f, however it's computationally expensive to evaluate. So additionally, we will group all of the terms in the integral, so the molecular orbitals and the exponential terms, by their indices, and we can factor the fourth order sum into a product of four first order sums, denoted here by g minus and g plus. The g minus and g plus terms can be noted as the traces of the Hartree-Fock-Green's function in real space and imaginary time, where the imaginary time coordinate is equivalent to the Laplace transform coordinate. All of the integrands in the methods that we're talking about here essentially have this structure of being products of traces of the Hartree-Fock-Green's function divided by the interelectronic distances. So the trace of the Green's function is a very algorithmically important object for these methods. It, of course, depends on the molecular orbital amplitudes as well as the molecular orbital energies. The molecular orbital amplitudes, in turn, depend on the molecular orbital coefficients and the atomic orbital amplitudes. With a computationally convenient expression for the energy integrand, we now need to establish a suitable sampling function. The sampling function for these methods is largely inspired by the Laplace transformed expression for the energy. Here is the direct term from the previous page. The important thing to note about this expression is that the integrations over R1, R2, R3, and R4 and the imaginary time coordinate can be performed separately. Because of this, we factor our sampling function into a product of three component functions, one each for the electron pairs and one for the imaginary time coordinate. The sampling function for the electron pairs is a product of two functions g that model roughly where the electron density is and are divided by the inner electronic distance. This is to cancel the same term in the integrands. And a suitable function for the imaginary time coordinate is an exponential distribution. This talk wouldn't be particularly interesting if we had only implemented MC MP2. Currently, we have implemented integrands for perturbation theory through fourth order, Green's function through third order with both diagonal and non-diagonal self-energies, and we have F12 corrections for both of the second order methods. We also have multiple sampling methods as well as various acceleration techniques that we've implemented, and we maintain GPU and CPU implementations from the same code base. To expose the classes that are the building blocks of our program, I want to look at the execution of our program to accumulate a single set of samples. The first step is coordinate generation, and based on the MC MP2 derivation that we just went over, this functionality is split into two classes, one for the electron pair coordinates and one for the imaginary time coordinates. The electron coordinates feed into our atomic orbital engine. Some might have noticed that in this diagram we only list two coordinates, whereas our MC MP2 integrand took 4 electron coordinates. This is resolved by the fact that we are actually batch calculating many pairs of electron coordinates at the same time. Next, we feed all of the atomic orbital amplitudes into our molecular orbital engine, which stores the molecular orbital coefficients, metadata about the molecular orbital amplitudes, and all of the sets of molecular orbitals, which are internally stored in a map. They're stored in a map because for the F12 methods, we need to add additional sets of molecular orbital amplitudes for an extra electron coordinate, as well as derivatives of the molecular orbital amplitudes. Then all of the molecular orbital amplitudes, as well as the exponential factors, are fed into a Green's function trace engine, which internally automatically resizes based on what integrands that we need to calculate in the next step. All of our energy integrands are provided by separate classes, but they all have one common interface, and this allows us to build up an array of energy functions that we want to evaluate for a particular MC run. Each of the blocks in this diagram represents elements that we can change to achieve the desired functionality. We've done the most work for the energy functions, closely followed by the imaginary time generator and the electron pair generator. The remaining classes have single implementations, but could easily be refactored in the future to implement more functionality. Before looking at the internals of some of these classes from a high level, I want to briefly comment on how we maintain the GPU implementation of the program. The first change is to allocate all of the memory on the GPU device rather than on the CPU. Coordinate generation is still performed CPU side, and then we copy the results to the GPU device. We have a custom implementation of the atomic orbital engine for the GPU. The remaining 3 sets of classes make heavy use of BLAS calls and their expressions. So by simply switching which BLAS library we link against these classes largely convert to run on the GPU with no other modification. The first class that I want to look at is the electron pair generator. The base class for this stores the electron pair weight as a private member variable and mandates that all implementations have a function called update that takes the two electron pair coordinates as in and out variables. In terms of actual implementations of this class, we have a metropolis generator, which has been the generator that most of the work for these methods have used. Very recently, we published an algorithm to sample the S-type Gaussian-based weight function directly, and this leads to a factor of 2 to 3 increase in efficiency over the metropolis generator by eliminating some autocorrelations. In terms of future development for this class, the most straightforward path would be to implement new generators such as a Hamilton Monte Carlo generator. Additionally, the electron pair weight class is defined through an abstract interface, and we could investigate sampling from new distributions for these coordinates, although such distributions would likely only be compatible with the metropolis generator. Next, I want to look at the classes that perform the imaginary time coordinate generation. Superficially, these classes are very similar to the electron pair generators, the most notable difference being that they store the coordinates as well as some of the derived values internally, and because of this, the update function takes no parameters. We have two instantiations of this class as well. One performs generation based on a quadrature rule, and that's the reason that the update function returns a bool, so we can loop over the quadrature points. The second instantiation is stochastic and provides points distributed according to an exponential function. In terms of future outlook for this class, I largely suspect it will be mostly stochastic generators with alternate probability distributions. Finally, we have the classes that define our integrands, the energy functions. These classes have more of a three-layer system. The top layer is an abstract class that allows us to store all of the energy functions in one array, and it largely contains metadata information. Below this, we have what I'm going to call a standard function, so this would be like MP2 or GF3, and it defines that all implementations need to provide an energy function that takes the Green's functions traces, as well as the electron pairs and the imaginary time coordinates. Alternatively, we have a second interface for the F12 functions. These integrands take no imaginary time coordinates, but do have an additional electron coordinate, so they work with the wave functions directly, and it's just a slightly different call.